A Chinese rover quietly uncovered something beneath the Martian sands, 76 mysterious layers that could rewrite everything we thought we knew about Mars. For decades, Mars was seen as a cold, dead world. But China's first interplanetary mission, Tianwen-1, changed that story. Beneath the dusty plains, scientists detected signs of ancient floods, buried ice, and salty crusts, evidence that liquid water may have lingered here far longer than anyone expected. And if water was there recently, what else might have been? It began on July 23, 2020, when China launched its first fully independent Mars mission, Tianwen-1, a single spacecraft carrying an orbiter, a lander, and a rover, all built domestically. No foreign assistance. No NASA blueprints. After a 7-month journey through interplanetary space, Tianwen-1 reached Mars orbit in February 2021. 3 months later, on May 14, 2021, its lander touched down in Utopia Planitia, the same vast plain where NASA's Viking 2 had landed 45 years earlier. Riding aboard that lander was the Zhurong rover, named after the Chinese god of fire. Standing 1.85 meters tall and weighing 240 kilograms, it became the first non-NASA rover in history to operate successfully on the Martian surface. It was designed to last 90 sols, roughly 3 months on Mars. Instead, it rolled, scanned, and transmitted data for more than a full year, covering nearly 2 kilometers before entering hibernation in 2022 when thick dust and the cold Martian winter dimmed its solar panels. A modest start, but what it found under the surface stunned even veteran scientists. Zhurong carried a ground-penetrating radar capable of scanning 10 to 35 meters deep into the Martian crust. Beneath the top layer of dust, the radar revealed something no one had ever seen before: 76 distinct horizontal layers. Each layer represented a shift in the environment, perhaps a floodplain, an ice sheet, or a period of heavy dust deposition. Scientists from the Chinese Academy of Sciences concluded these patterns point to episodic flooding events where ice melted, flowed, and froze again over hundreds of thousands of years. The rover's other instruments found minerals that only form in the presence of water, including hydrated sulfates and salts. These create thin, salty crusts that trap moisture and could once have allowed liquid brines to exist just beneath the surface, even in Mars' freezing conditions. And perhaps most intriguing of all, the textures of nearby dunes told another story: signs of recent glacial or periglacial activity, reshaped sand, cracked crusts, and smoothed ridges that likely formed as recently as 400,000 years ago. To put that in perspective, that's not ancient in planetary terms, that's when early humans were already walking on Earth. For decades, scientists believed that Mars's last liquid water disappeared billions of years ago. Zhurong's radar changed that timeline completely. The discovery suggests that liquid water and potentially habitable conditions persisted much longer, perhaps well into the planet's recent geological history. That means the window for life on Mars might not have closed billions of years ago. It might have lingered, flickering under the ice, just beneath the dust. And that single finding from a rover few expected to succeed has reframed the entire search for Martian life. Because now the question isn't whether Mars ever had water, it's how long it lasted, and whether something might still be hiding down there. Nearly half a century before Zhurong's landing, humanity first tried to answer the ultimate question: is there life on Mars? In 1976, NASA's Viking 1 and Viking 2 landers touched down on the red planet. Each carried a miniature biology lab, the first of its kind beyond Earth. Their mission: to scoop up Martian soil and see if anything inside was alive. The experiment mixed the soil with nutrients labeled by radioactive carbon. If microbes were present, the gas released would betray their activity. And when Viking sensors lit up, they did find something. But when the data was analyzed, scientists were divided. Some said it was life. Others said it was just chemistry. The surface of Mars, it turned out, is soaked in perchlorates, reactive salts that mimic the signatures of biology. The debate raged for decades. Did Viking accidentally kill the very microbes it was trying to detect? No one knew for sure. Mars wasn't always this cold red desert. In fact, its climate has swung wildly over millions of years, from icy stillness to bursts of flowing water, all driven by a natural rhythm written into the solar system itself. Scientists call these shifts Milankovitch cycles, predictable wobbles in a planet's motion that change how sunlight falls across its surface. And Mars, with its unstable orbit, feels these cycles even more dramatically than Earth does. First, eccentricity. Every 100,000 years or so, Mars's path around the Sun changes shape. Sometimes it's nearly circular. Other times, it stretches into a long ellipse, bringing the planet much closer to the Sun on one side and much farther away on the other. When that happens, the difference between summer and winter becomes extreme. One hemisphere bakes while the other freezes. And during those warmer phases, buried ice can melt, seep, and refreeze, leaving behind the layered sediments that Zhurong's radar picked up beneath the surface. Those 76 underground layers may actually be a record of Mars's orbital heartbeat, one layer for every great swing of its eccentric orbit. Then there's the tilt, or axial obliquity. Right now, Mars tilts at about 25 degrees, almost the same as Earth. But unlike Earth, Mars doesn't have a large moon to steady it. Over hundreds of thousands of years, its tilt can swing between 15 degrees and 35 degrees, a massive wobble that completely reshapes its climate. When the tilt grows larger, sunlight reaches deeper toward the poles, melting polar ice caps and pushing vapor and frost toward the equator. When the tilt decreases, the planet cools again, freezing that moisture back into the ground. Zhurong's radar layers and chemical data, salty crusts, frozen brines, and water-altered minerals, line up perfectly with this pattern. It suggests Mars went through repeated cycles of melting and refreezing over and over as its tilt shifted through time. And then there's the slowest cycle of all, precession. As Mars spins, its axis wobbles slightly like a spinning top that's starting to lean. That wobble changes which hemisphere points toward the Sun during certain parts of the orbit. It's a small motion, but over tens of thousands of years, it can shift where the warmest regions on Mars are, swapping mild seasons from north to south. That constant reshuffling may have helped redistribute water and dust across the planet, shaping the dunes and deposits that Zhurong explored. Together, these three movements, eccentricity, tilt, and precession, act like gears in a cosmic clock. Each tick melts ice, shifts winds, and buries new sediments. Zhurong's radar data fits perfectly into this rhythm. The 76 underground layers may represent cyclical periods of melting and refreezing, each layer a snapshot of a warmer, wetter Mars, repeating over hundreds of thousands of years. That means these floods weren't random events, they were part of a planet-wide heartbeat, the pulse of water ebbing and freezing through deep time. The next chapter in China's Mars story is already being written. It's called Tianwen 3, Questions to Heaven, Part 3. Scheduled to launch in 2028 and return samples to Earth by 2031, this will be one of the most ambitious robotic missions ever attempted. It will use two Long March 5 rockets, one to deliver an orbiter and return vehicle, and another to send a lander and ascent module to the surface. Together, they'll attempt to collect pristine Martian soil and rock and then shoot them back into space for the journey home. Chinese scientists have identified 86 potential landing sites, focusing on Utopia Planitia, where Zhurong made its discoveries, and Chryse Planitia, home to ancient deltas and dried lakebeds. These areas are geological treasure troves where biosignatures, the chemical fingerprints of past life, are most likely to be preserved. Tianwen 3's lander will carry an automated drill and sampling arm capable of reaching multiple depths. It will collect both surface dust and subsurface material, sealing them inside sterile capsules. Onboard instruments will screen for organic molecules, hydrated minerals, and possible microfossil textures before storage. Once sealed, the ascent vehicle will blast off from Mars, rendezvousing with the orbiter waiting above. That orbiter will then begin the long return to Earth, delivering the first ever Martian samples directly into our laboratories. And this time, China says the results won't be kept behind closed doors. The mission is designed for international collaboration, with scientists from around the world expected to analyze the returned material together, a symbol that Mars belongs to all humanity, not just one flag. If successful, Tianwen 3 could deliver humanity's first physical Martian rocks to Earth years before NASA's own sample return, which has been pushed back by funding cuts and logistical setbacks. NASA and the European Space Agency once planned to retrieve Perseverance's cached samples by the early 2030s. Now, those plans are in doubt, opening a narrow but historic window for China to seize the lead. If their samples reach Earth first, and if they contain even a trace of organic chemistry, it would be nothing short of revolutionary. For the first time, we wouldn't just be looking at Mars through robotic eyes, we'd be holding pieces of it in our hands, perhaps holding the story of life itself. While Zhurong slept beneath the dust of Mars, back on Earth, China was already building Mars. In the Gansu province, on the edge of the Gobi Desert, stands Mars Base 1, a $61 million facility built in 2019. Its red sand hills, pressurized habitats, and glass-domed greenhouses make it one of the most realistic Mars simulations on Earth. Originally launched as both a training ground and a tourist attraction, Mars Base 1 hosts Chinese students and astronauts in training to rehearse what life on the red planet could be like, complete with mock airlocks, solar labs, and even simulated dust storms. Further west, deep in Qinghai's remote desert, lies Mars Camp, a far more rugged prototype. Unlike the glossy domes of Gansu, Mars Camp is a cluster of metallic modules and repurposed shipping containers arranged like a frontier outpost. It's meant not to impress, but to prepare. Here, engineers and young recruits practice patriotic education, learning to survive isolation, ration air and water, and maintain critical systems, skills they might one day need 200 million kilometers away. Together, these two Earthside bases mark the first stage of China's Mars colonization plan, building the mindset before building the mission. And the roadmap itself is already drawn. China's space agency has outlined a series of 5 crewed Mars missions spaced roughly 2 years apart: 2033, 2035, 2037, 2041, and 2043. The first missions will test life support, landing, and ascent technologies. Later ones aim to establish permanent surface habitats and in situ resource extraction, using Martian soil, ice, and atmosphere to produce fuel and oxygen. To get there, engineers are designing a nuclear-powered spacecraft, not a science fiction concept, but a real propulsion system already under development. A nuclear thermal engine could offer double the efficiency of chemical rockets, cutting travel time to Mars nearly in half while providing constant onboard energy for the crew. But propulsion is only half the equation. The other half is logistics, getting the sheer mass of equipment into orbit. That's where the vision of a sky ladder comes in, a theoretical space elevator stretching from Earth's surface up to low Earth orbit, built using ultra-strong carbon nanotubes. In theory, cargo could be lifted into space at a fraction of today's cost. No rockets, no fuel, just gravity and counterweight. It sounds impossible, but the same was once said about reusable rockets and landing on the far side of the moon, both things China has already done. While China's ambitions are methodical and state-driven, on the other side of the Pacific, another contender is racing toward the same goal: Elon Musk and SpaceX. Musk envisions a self-sustaining Martian city of 1 million people by around 2050, ferried there by a fleet of starships, each capable of carrying 100 tons of cargo. China's plan is more centralized, slow, and strategic: fewer risks, fewer public updates, but immense coordination between government, military, and private industry. SpaceX's approach is the opposite: rapid iteration, transparent testing, and public trial and error. Different philosophies, same bottleneck: how to move vast amounts of mass into orbit and then across the void to Mars. Whichever system cracks that problem first, reusable rockets or a sky-high elevator, could define the next century of space travel. The next great leap is already on the calendar. By 2031, Tianwen-3 will return the first-ever Martian samples to Earth. Inside those tiny sealed capsules may lie the answer to one of humanity's oldest questions: are we alone? If China brings back the first evidence of life beyond Earth, even a single microfossil, a molecule, or a hint of biology, history will remember that moment forever. But this story isn't over. Because as China prepares to bring Mars home, it's also preparing to go there itself. So the question now becomes, what happens if China colonizes Mars before anyone else? Subscribe to the channel. Do you think life still hides beneath the Martian surface?